So let's begin. So last time, right, we covered the uniform distribution, right, and the exponential distribution. The one thing that is probably helpful, right, to remember about the uniform besides, of course, the expectation and the variance, is the fact that the uniform acts like a equilikely, right, sample space in a continuous version. So for the uniform to calculate probabilities is just like calculate proportions. For the exponential, right, of course, that's not the same because the exponential, right, doesn't have constant density. But the exponential, right, has its own properties. The first thing, right, is that basically knowing the expectation and the variance of an exponential allows you to, right, simplify certain calculation, right, that would involve integration by parts, okay, by associating correctly the integral with an expectation, right, of an exponential random variable. The second thing, right, is that basically an exponential, right, is actually the only random variable, okay, with the so-called memoryless property, meaning that if you model some time of an event as an exponential, what that means is that you are committed, right, to saying that if the event hasn't happened after some time, given that knowledge, doesn't matter how large t is, and that's also like kind of an interesting thing. Doesn't matter how large t is, then the fact that you have to wait an extra h unit of time for the event to happen is the same, right, as if you start at the beginning and wait for the event to happen, right, within h units of time. And so again, right, that may or may not be what you want. But if the event that you model doesn't seem to exhibit, right, this property, then, right, the exponential may not be a useful or may not be an appropriate, right, random variable to use. Okay. And in terms of the problems, right, we looked at the well, this one is just a standard one, but we looked at this one, right, where basically is to find the value, right, that minimize the absolute distance between the random variable and the value, right? And the random variable here in question is the exponential, but this is true in general, that the method would yield the answer as the median, okay, of the distribution. In other words, right, the value that's 50% of the distribution is to the left and 50% of the distribution is to the right of the value. And sometimes, right, this value coincides with the expectation, right, the average, when the distribution is symmetric, like the uniform. So we solved this question before, right, with the uniform, and we got the answer to be the expectation of the uniform. But here in this case, right, with the exponential, we see the difference. They are not the same, okay? Okay, so now let's move on to I guess the last major random variables that we need to cover, right, for this course, which is the normal, right, which is probably the most famous anyway. So for a normal, right, random variable, then the density, right, is the famous bell-shaped curve, right, like that. And the peak, right, is exactly at the mean, right, and the spread, well, you could say something about the spread, but the larger the sigma, right, the more spread out, right, the normal curve is. And of course, right, it's designed exactly so that the expectation is mu and the variance, right, is sigma squared. all of this, right, of course, can be done by, integrating, right? And with the normal, you would do basically a U sub, or if you have to calculate the variance, right, you have to do integration by parts. But anyway, right? So the normal is so well known that basically you see it in many, many places, right? But what is it used for? What is it like a proper model for? And so again, right, the word proper probably, right, depends on the situation. But most of the time, or like I guess the main use is to model the error, right, you commit in a in a measurement, or like white noise, right? So why is that the case? So for example, right here, you would see, right, that when you take a linear regression class, then the error that remain after you kind of run the regression, right, of y based on x on the axis would be modeled as a normal random variable, right? Why is that the case? The reason actually where this is intimately connected to, right, the central limit theorem, which is like one of the two major theorems, right, in probability. The other one being the law of large number. And we will talk about the central limit theorem soon, like right now. But basically, right, the central limit theorem says roughly that the average value, right, let's take a look at the form. The average value in some way, right, the scale here is root n, but you can kind of view that as an average. The average value of IID, meaning independent and identically distributed effect, will converge to a normal distribution, right? That's all we want to say right now. And so that's why it tends to have that kind of effect in terms of the error modeling. Because when we look at error, we kind of think of the error as resulting, right, from the average of many, many effects, right? That is unaccounted for, right? So when you take a measurement of something, let's say in physics, right, the difference between your measurement and the true value, right, the measurement, the true error, right, would be the resulting of many factors. I don't know, environment, your reading of the instrument, and whatnot. And the average effect of that could reasonably, right, because the independent, whatever, right, say to be modeled as a normal. Of course, you see, there's a lot of jump, right, about this and that. But of course, like standardly, right, it seems okay to start using the normal to measure, to model the error, right, from the average effect. Okay, that's kind of the main thirst there, right? That error usually comes from the combination of different effects, independent effects. So therefore, by central limit theorem, we could use a normal, right, as a model for it. Okay, so one more thing, right? It should go without saying that you cannot integrate, right, a to b f of x dx for the normal random variable using, right, calculus techniques, right? The reason is because the function.
What are you saying with the link? Sorry, what are you saying about the link? Oh, is it better to go 30?
Someone forgot to mute their mic.
Right now, we're going. 9. You mean to get that? 21. Yeah, it's like you didn't understand because there is basically the one right before suburban. Yeah, I saw a couple groups of people going to the 30. You take the train over the bridge.
Okay. So right, where were we? So yeah, right, the function, right, e to minus x squared or x squared over 2, whatever, right, does not have an antiderivative, right? So does not have like a analytical antiderivative, So questions about computing probability of a normal random variable, right, doesn't have to come up theoretically, right, in this class, because there's no antiderivative, so we don't formulate. We could, right, we can still talk about it, but the answer will be normally, right, symbolically written as the CDF of the normal random variable, right? And we'll talk about like the Z transformation to scale it back to the standard normal. But yeah, calculating the probability of a normal random variables usually, right, do not come up as a question. Well, back in the time, right, back in the day, you would be taught the technique of reading, right, the normal table. But I guess those kind of skills are not needed these days, right? So we'll just kind of wipe it right under the table. So, yeah, so let's talk about the central limit theorem, right? So the central limit theorem is one of the two major theorems in probability, the other one being the law of large number. It's important, right, to get the form of the theorem correctly. So what it says, right, is if you take a sum of independent random variables and you scale it properly, then it will converge to a standard normal, right? So the normal 0, 1 is also referred to as Z standard normal, right? The letter Z without, I mean, when you're referring to a normal context, would always, right, conventionally stand for the standard normal 0, 1. So let's take a look, right? The subtract mu and division by sigma, right, is called the Z transformation. Right, this is one of those things that exactly is a translation and a scaling, right? We kept talking about translation and scaling, right, for the uniform and the exponential. Here it is again, right, translation and scaling. But the translation and scaling here, right, has the normalization effect, right? I mean, the word normalization here, not sure if it's connected to the normal, but you know, probably it is, right? But the normalization here can be used for any random variables. So if you subtract the mean and divide it by the standard deviation, the effect is that you will make, right, the expectation into 0, right? Because of linearity of expectation. And you will make the variance, right, into 1 because of the rule of the variance, right? Okay. So normalization, right, ensures that at every step, you are adding, right, a bunch of random variables with mean 0 and variance 1, right? Okay. Then why the scaling over root n? The scaling over root n is yet another kind of normalization with very, very specific intention, right? Because, for example, if you look at the variance of this sum, right? Because the sum is independent, because the terms are independent, right? The sum of the variance of the sum is the sum of the variances. But we just mentioned how each of the term has variance 1. So this variance is n, right? But if you divide by over 1 over root n, right, the effect is if you factor it out, right, it becomes a square. So that's n over n. So that's 1, right? So there you have it, that basically, right, that this scaling right here ensure that the variance of this is always 1. And of course, right, because each term has expectation 0, right, the sum has expectation 0, divided by over root n has expectation 0. So the scaling, right, guarantees that this sum always has mean 0 and variance 1. And so by the mixing property, what that means, it converges to the standard normal, right? We'll look at the proof of this more closely when we look at the moment sharing function section. But for now, right, that's what you want to pay attention to, the scaling factor and the translation factor, right? That somehow keeps everything always stays 0 and 1, right, for the mean and variance. Any question about this? All right. Now, though we won't have a, well, we might have something to do with the general central limit theorem in this class, but a lot of applications will again focus on the binomial, right, approximation, or the normal approximation, right, of the binomial. Remember, right, we had the Poisson approximation of the binomial. Now we have the normal approximation of the binomial. And maybe, right, the only thing worth talking about here is why does it work? Well, why it works is kind of obvious because, right, we mentioned that the binomial is a sum, right, of independent Bernoullis. And that's why it fits perfectly into this framework, right? You are summing IID random variable. Now, on the other hand, right, you can also ask, well, what are the scaling, right? Because the scaling here and the scaling there doesn't look the same, right? Well, you can write the scaling in many ways and the translation, right? But the effect of the scaling and translation is to make the expectation 0 and the variance 1. Okay, let's take a look. The binomial NP, of course, has expectation n times p. When you subtract that, expectation here is 0. So there, that explains the term n times p, right? The binomial NP has variance NP1 minus p. So if you divide by the standard deviation, you make the whole term having variance 1. So that's it. That explains the translation and scaling in specifically for the binomial, for the normal approximation of the binomial. All right, any question about this? Right. Again, right, the reason why the approximation is relevant is because, right, if you have something like 500, right, choose 50, or 500 choose 100, right, and then p to 100, 1 minus p to the 400, right, where p is small, right, p is 0.1, that kind of thing. So again, right, notice, I guess another thing here is that, notice that here p doesn't have to be small, right? P can be anything. So p can be 0.5, right? Unlike the Poisson approximation, right? This actually works well for p large or p in the normal range. But still, right, 0.5 raised to the 100 is actually a rather small number. 500 choose 100, again, is a very large number, right? So without some well-formed approximation, doing this calculation, even in this day and age, right, without the help of some tool, right, will yield a inaccurate answer. Okay, and that's why we need the approximation. Okay, so that's the sort of the statement, but it needs a refinement. The refinement is the so-called continuity correction, and we will always do this. All right, and that's probably the only thing that maybe is slightly more difficult beyond applying the formula. So the continuity correction means that you cannot use a straight number here. So here, yes, this is kind of what we write here, right? But we write it here just to kind of express the fact that this converges to a normal, okay? But if you, for a fixed, and also it has a limit here, right? But for a fixed value, when you want to approximate it, then you need to do some change to the value k, all right? And that's a continuity correction. And so here's the thing, right? Basically, why the continuity. So okay, let's state the continuity correction first, and then explain why. So basically, right, this is one way to do it. But in general, if you have probability of a less than equal to x less than equal to b, all right, and x is the binomial here. All right, and a, b are integers. Okay, because the binomial can only take integers value. Notice is equality on both of them. All right, equality on both ends. Now, equality, remember, matters for the discrete distribution. Okay, it doesn't matter for the continuous distribution. And that's exactly the reason why we need continuity correction. Because equality matters here, it does not matter for the normal, or you're moving from a discrete random variable to a continuous random variable. So that's something that you kind of have to adjust there. And the adjustment is something like this. You can say equal a minus 0.5 less than x less than b plus 0.5. And then from here, you can move to the standard normal by subtracting np and divided by square root n minus p. So that's the continuity correction in the nutshell. Okay. Now, why is this so? Why this is so, right? We'll have a next slide to explain in more details. But as you can see, because x is a random variable that takes on integer values, and a is an integer, subtracting 0.5, right, doesn't change anything. Because, right, x does not take any value from between a minus 0.5 to a, right? And x does not take any value between b to b plus 0.5. So changing this does nothing. That's why it's equal, right, to the expression. But it means a lot when it comes to the z distribution. Because with the normal, right, it will see the difference of a gap of 0.5. So that sort of is the intuition in a nutshell to begin with. Okay. Any question about this? All right. So now, to explain why, right? The y actually is right here, or like that, right? The probability x equals to 5 in the binomial will have a positive probability, right? However small, it is a positive probability. But if you somehow if you move that to probability as standard normal equals to some value, then that's 0, right? So this makes you approximate the probability, the binomial, right, equal to a value to be incorrect, right? Because you want to approximate a very small number with a very small number. But if you always use 0 to approximate it, that's a gross error. So that's really it, right? Basically, it starts from the fact, right, that the discrete random variable takes on some discrete value with positive probability, while a continuous random variable taking on a corresponding value with 0 probability. So we want to adjust, we want to open up the window so that, right, you have some room for the continuous random variable to take on value. Okay. Any question about this? All right. So, right, we did mention, right, the translation and scaling, or the Z transformation, but let's mention it one more time, right? So basically, right, the normal stays normal under translation and scaling, right? You just have to calculate the corresponding mean and the corresponding variance correctly. But before, right, when we talk about translation and scaling of the uniform, let's say, then that's just some discussion. Here it has a special meaning, right? It has a special use, because when you want to calculate probability of like this, right? Let's say less than or equal to some value, okay? Then back in the day, at least, and even now, right? What you want to do is to use the Z transformation to translate it back to the standard normal. And then, right, look up the normal table, or look up, right, the, let's say the normal function, right, in a package, like, I don't know, a Python package, right, for example. So this N notation here, right, you can use other notation like F sub Z, let's say. I think that probably is a bit more big F, right, big F sub Z. But some circle use the big N notation, right? That stands for the CDF of the standard normal, right? And that's all you do. Okay. So you convert, right, the probability or the CDF or whatever it is, right, of a general normal to this probability of a standard normal. And you express that in terms of a CDF. That's all you do, okay, to answer questions, because then you can look up such a CDF as a built-in tool in a package, in a statistical package. All right, and that's the importance and meaning of the Z transformation and being aware of the standard normal. Any question about this? All right, so let us take a look at the problems. All right, so we start out, at least for the first question, right? It's just meant to ask you to use the Z transformation. Okay. And again, in a question like this, right, back in the day, you're supposed to come up with a numerical answer. We don't do that here, right? The goal is to use the Z transformation and then rewrite everything as a CF of a normal, of a standard normal. Okay, and that's all. No more than that. Right. So because there's nothing interesting here, right? Let's just show you. So that's the answer, right? In terms of the CF of the standard normal. Okay. And then I think, I guess I missed this, but there's the extra question that it will take more than 10 years before blah, blah, blah. That would kind of repeat that, but into a binomial distribution. Okay. But what I want to say is, right, a question like this, again, right, do not require any kind of numerical answers. What you have to do here is just to use a Z transformation, right, to get it back to a form that is acceptable. Do you understand? And then, right, I mean, just to show you what the full solution would be, you know, you got that and you got the numbers, but it's not needed. All right, any question about this? All right. Again, right, the second question is something of the similar nature, right? But here is probably, right, back in the day where you have the, let's say, the tail end, right, probability of the random variable, you know that number. It wants you to deduce the variance, right? So you just kind of want to go through the procedure and see how you would logically, right, figure out the variance from there. All right, so what procedure should we follow to find the variance with these numbers? What you always do, right, is the Z transformation to convert everything to standard normal, right? So probability x bigger than 9 is probably x minus 5, right? Divided by sigma is bigger than 9 minus 5 over sigma, right? Equal to 0.2. Okay? Which is the 1 minus, right? The CDF of the standard normal. Okay? And so the second step then, right, of course, is then, right, the CDF of this value is 0.8. So the second step is from here, you figure out what this is. That's a procedure, right? You look back, right? You look at the normal table and figure out what value, right, in the normal table that would yield a probability CDF of 0.8 for the standard normal. All right. And then you will solve for sigma or sigma squared rather, right? That's it. That's a procedure. No numerical values involved. I mean, besides, of course, right, whatever the problem gives. Any question about this? Okay. All right. So this one actually, right, will be more important or more interesting. So let's give it some time. Okay, so there are two questions to this, right? Actually, there are two questions, right? The first one is about computing this probability, right? So the random variable, right, is the number of 6 appearing, right? And in this context, it should be clear that it's a binomial, right? 1,000, 1/6. And so the question asks for a probability that is between 150 and 200 inclusively, right? Again, these things in this particular context have to be done precisely because of the continuity correction, right? So where else you make a small mistake here in terms of inequality, that's still an error, but might be less. Here, right? Is this the point of the question, where you miss or not miss the inequality, right? Will change the spirit of the problem. All right, but then let's see, right? How would we convert this to the normal approximation? What would that be? So remember, right? The continuity correction is like that, or right, like that. Okay. And so you would correct this to 149.5 to 200.5. Okay. And notice this is still x, the binomial, right? I'm not doing the normal approximation yet. Now the normal approximation would be subtracting the mean, right? Divided by the standard deviation, and then standard normal here, subtracting the mean, and divided by standard deviation, right? What the mean is, and the variance is, right? Any question about this? And of course, right, you can write this as the CDF at the right point, subtract the CDF at the left point. And that's it. That's the continuity correction for the first part. Are you okay with this? All right. What about the second question? First of all, right, what kind of question is the second question? It is a conditional probability question, right? That basically says the number. So it's really a separate question, right? If so, you basically we don't have a random variable yet, but it says something like probability 5 strictly less than, right, 150, given that number 6 happens exactly 200 times. Okay, so it's a conditional probability question. Now, of course, the point here is not about, right, a binomial conditional probability question, because we know how to write that down. But the question is in the context of the normal approximation. How would we apply the normal approximation to handle a conditional probability calculation? Or let's put it another way, right? So far, the normal approximation we talked about is for the binomial, right, random variable. In the second question, what binomial are we talking about? What is the binomial random variable that we can use, right, for normal approximation in part B? What should be? Is it the same binomial as we use in part A? Just try to say it's less than 150. Or is this something else? It cannot be the same binomial as we used in part A, right? The reason is this is an unconditional probability, and this is a conditional probability question, right? So it cannot be the same. Or if it's not the same, then what is it? All right. So the answer is, right, what we have to deal with here is a binomial that results from the conditioning. That is, right, that basically, if you let X, or let's call it Y here, you let Y be the number of 5 that appears, right, given that number of 6 appear 200 times. Okay? So because the information that's given cannot be changed or is a fact, right? So the number of 6 appearing is 200. What that means is that the number of, well, so what that means, right, is because you have already 206s appears, then the remaining, right, trials is 800. Okay. Now what happens within this 800 trials? Within this 800 trials, right, 1 to 5 would appear, right? But 6 cannot appear because, right, by definition, these are the 800 remaining trials. But 1 to 5 would appear equally likely, right, in this remaining 800 trials. So what we have here is that Y will be a binomial 800, but with success probability 1/5. Do we understand? So that's the random variable we're dealing with. And that's the random variable we will use the normal approximation on. And so, right, we will look at probability of Y strictly less than 150. Now you still have to do continuity correction here, right? But what would the continuity correction be? Just because it's strictly less than doesn't mean you don't have to do it. But what would the continuity correction be? So the way to do it, right, is Y less than or equal to 149.5. Sorry, 149, right? Because strictly less than 150 is less than or equal to 149. And then you can use the continuity direction from that, because you know this is exactly Y less than 149.5. Right, so the point is 149.5 is the continuity correction. Okay. And then, right, you can convert this to a standard normal, less than 149.5 minus mu over sigma, right? But this mu here will be 800 times 1/5, and sigma square is 800 times 1/5 times 4/5. right, you understand? Any question for this? Okay, so let's take a look at this question. All right, so this kind of question, right, is kind of right in the hypothesis testing circle, right, or topic is called type 1, type 2 error kind of calculation question, right? Or basically, false positive and false negative, that kind of question, right? So if it's actually fair and we reach a false conclusion, I guess that's a false negative, maybe, right? Because we say that it's not fair while it's actually fair, right? And the other one would be a false positive, right? But yeah, so yeah, right. So this is exactly hypothesis testing, right? We say the coin is biased if it's more than 5 to 525, right? Inclusive, right? So it's really just about calculating probability, right? That X is the number of heads, right? It's big and equal to 525, condition on, right? Let's say fair. Sorry. Yeah, right, because we reached a false conclusion. So part A is that, right? Okay. And once again, right, this is just basically a normal approximation with the right continuity correction. So let's move there directly, right? This is going to be probability that standard normal, right, bigger than 524.5, right, for the continuity correction. And minus mu, right, divided by sigma, right? Where mu is, so we do the test 1,000 times, right? So 1,000, right? But the coin is fair, so it's 1/2, right? Sigma square is 1,000 times 1/2 square, right? All right, any question about this? All right, now the opposite, right, is less than 525 given bias, right? That would be the conclusion, right? False conclusion if it were biased, because then we'll conclude that it's fair, right? And then again, right, it's still X, right? So Z, right, but now the continuity correction would be 524.5, right? minus mu over sigma, right? Let me make sure, right? Yeah, you subtract 0.5 from this one, that's correct, but this is less than, and because it's strictly less than, it's less than equal to, right? 524. So it's still 524.5, right? The continuity correction lands at the same number, right? In both cases, okay? But here, right, mu would be what? Mu would be 1,000, right? But the bias coin is 55%. So times 0.55, and sigma squared is 1,000 times 0.55 times 0.45. Okay. Any question about this? All right. If not, then I think let's give you the quiz, and then we'll continue, right, at 7:05. All right. So the quiz will be on this question. Any question before we take a break? All right. So let's continue at 7:05. Okay. All right, let's continue. Is there any question before we continue? All right. So where were we? So we did the bias coin. All right. And then that's that. Yep. Okay. So I think now we can go to the last part of the lecture. Okay. Well, so this is just some materials to mention. So the point, right, is the concept is the median, right, and the quantile of a random variable. We talked about the concept before, right, about a median, right? So the median, right, is the quantity. I mean, right, there are many notations, right? I just only use x sub 0.5 here to distinguish it from other values, but right, different people might use different notation. But basically, right, it's the value that 50%, right, is below the value and 50% is above the value. Now, the reason why, let's say, so far we did not discuss the median or the median, right? Let's say it's not an awkward concept; it's a very, very, very good concept to know. But there's ambiguity, right, when it comes to discrete random variable on what the median would be, because right, there would not have, let's say, right, an exact value that would split, right, 50-50, because the nature of discrete random variables is it has point mass, right? Of course, there's some convention, right? About how to split it, but let's say that's a convention, right? So the ambiguity is there, let's just say. But for a continuous random variable, right? The benefit of a continuous random variable is you always have a precise value. Okay, so that's actually a concept that, at least in theory, you should be able to find, right, for any continuous random variable, what the median is. And right, the median actually, so this concept, like I said, but it sort of is more useful, right, in a statistics class, because there you want to estimate parameters. So, right, the sample median and those kind of things come in handy, right? And the concept that's connected to it is called a robust estimator, meaning that it's not as influenced by outlier as the mean, for example. Right. So similarly, right, we can extend, right, the median to a quantile notation by changing the 0.5 to some other, right, probabilities. And so depending on what you want, but usually they associate a quantile with the right tail, okay? Meaning that the probability is less than that is alpha. So be careful, right? So for example, right? So the 0.01 quantile, right, means this is 0.01, right? And 0.99 quantile, right, is over here, right? Meaning 0.01 is above it. I'm not sure if you guys still take SAT and that kind of exam these days, right? But any standardized exam, right? I think you would know your percentile, I think, right? Meaning how many what's percentage of the population scores above you and what's percentage of population score below you, right? So that kind of thing. So that's this kind of concept. But again, right? So for the distribution, then for as far as we are concerned, right, the same story happens that for a discrete random variable, right, quantile may not exist, right, as a precise value, while for a continuous random variable it does, right? So like that, right? So you can find this precisely, right? The quantiles of the normal also are well known, right? The 90%, 95% are well known, right? Well known, but probably, right? I think I already forgot what those are. I think 1.98 somehow comes to mind, but I'm not so sure, right? It's been a while since I controlled the normal table. But yeah. Okay. Anyway, right? So the reason why you want to care about the quantiles, right, as a concept in general, is at least, right, one of the concept here is called the QQ plot, the quantile plot. What it does, right, is it plots the sampling quantile or sample quantiles on one axis, and it would plot the theoretical quantiles on another axis. Okay, so basically, right, you would have the sample 25th quantile, let's say, and then you will plot it against the theoretical 25th quantile. So whatever, right, depending on how many points you have, data points you have. And the point here, right, is this plot can help you can help you give a statistical test for the hypothesis, right, that your data follows a certain distribution given by the theoretical quantiles, right? I guess most commonly is used, let's say, for a normal test, right? You have a certain data and you want to ask if it comes from a normal distribution. Well, what do? You plot the theoretical quantiles. Sorry, you plot the sample quantiles against a theoretical normal quantiles, right? And of course, right, if the dot lined up close to the x equals y line, that's a good sign, right? That's a sign that, you know, like, of course, the fluctuation, right, is due to statistical error. But, right, if it lies close to the line x equals to y, that's a good sign. If it's not, right, that's a bad sign, right? But of course, right, the point of the statistical test is to give you a rigorous standard on how far, right, it's too far, that kind of thing. Right, and also the QQ plot can also reveal some other interesting features. For example, right, a lot of times the data might look like normal. When you look at the histogram, right, it looks like this. All right, so it looks like bell shape, okay, looks like normal, but not quite. Because if you do plot the QQ plot, right, against a normal quantiles, what you might discover is that it looks like this. So basically, it looks okay in between, but out to the two ends, it diverges. Okay, so if you have something like this, right, this is called the big tail, right, or fat tail, right, phenomenon. And that signals that your data is actually not quite normal. It may be a T distribution or something like that, right? So again, I mean, these stories don't belong to a class like this. It belongs to like statistics and things like that. But we want to mention it here, right, in the context of basically being able to find, right, a quantile of a continuous distribution precisely. I think that's more of the message here, right? So the story we want to tell here is the quantiles in the context of discrete versus continuous distribution. Because you could, right, want to test you can do the quantile, the QQ plot, but for a discrete distribution. And you could imagine that you will run into some difficulty there, okay? Deciding the theoretical quantiles of the discrete distribution. Let's say you want to test something that looks like a Poisson, right? Then you have to look at the quantiles of the Poisson. The Poisson being a discrete distribution might give you some difficulties, right, in nailing down precisely what the theoretical quantiles would be. Right. Any question about this? Okay. So the last topic for this lecture is about how to find the PDF of a function, right, of a continuous random variable. All right. And this is harder than the discrete random variables because, right, the PDF is not a probability. So you have to work at the CF level, right? So the next few slides will give you a scheme to go through the steps, right? But so yeah, right. So something like this, right? Maybe let's pause here to see if So let's just kind of demonstrate, right? If you have a uniform distribution, would the square still be uniform?
No.
Yeah, that's correct. But any justification? For example, let's say you have a uniform 0 to 1. What would the square look like? Can you tell? If you can't, don't feel bad. That exactly is the whole point.
Is it parabola or?
Well, the parabola is from your intuition about parabola of function. So are you sure that so
No, I'm not sure. I
no, it's
think
fine, right? No, again, right? It's very natural for us to think about parabola too, but is it right? And we'll see, right? We'll see. Well, actually, I think we will have a solution down here. But the point, right, is that that's exactly it. You probably intuitively feel is no, but ask why or what the exact thing is, right? I hope that you'll see that you don't quite know. And that's the whole point, right? It's not meant to be easy because a PDF is very subtle, right? How to convert from the PDF to the probability, right? It's a not an easy question. Okay, so we'll see. But yeah, parabola, not so sure, right? So anyway, the programs as follow, right? Always start with the PDF. Sorry, always start with the CDF of what you want to know. Then you substitute in the expression for x into y, and then work out this in terms of x, and then deduce by taking the derivative. Deduce the PDF by taking on the derivative. Okay, so more like 4 steps, right? Start with the CDF of the ones you want to know, replace it with x, work out the expression, and then differentiate. Okay, so let's see, right? Yeah, so these are the steps in more details, right? But strong warning here, right? Step 3 is not always possible. The reason is, right, not all functions have an inverse. So here we'll just write step 3 kind of to show you what you could do to work it out, right? As in like transform it into x. But that a lot of times the steps are more involved. Okay, so let's see. So yeah, so here is the program in a clean step if you can do this. All right. But I strongly discourage the use of the formula here. You should always try to work everything out in the sequence of steps so you can control it. If you use a formula, I'm going to bet you're going to make an error, okay? Because you cannot control what's going on. But yeah, let's take a look. Right, so x squared, right? The first step is work with the CDF and then replace it with x, right? Y is x squared, so it's like that. And then, right, work out this expression. And you see, right, because this square function is not increasing, not 1 to 1. So this will become this. And then, right, of course, this in terms of the PDF of x will be like this. Okay. And then, right, you would differentiate this expression, right, in terms of y to find the PDF of X, to find the PDF, right, of Y. Notice this is a CDF of X. So when you differentiate, it becomes a PDF of X, right? Evaluate here. But then there's a chain rule because you have to differentiate what thing inside. So you get this. So the final answer is this for the PDF, right? So this is very abstract. This is true. Right, for any X and Y, right? But we'll work with more specific function. But any question about these steps? Going from step 1 to step 2 and then differentiate. Any question about any of this part? All right. So now let's go back to the uniform and see if you can make your guess a bit more precisely now. If X is uniform 0 to 1 and Y equals to X squared, then what does a PDF of Y look like? Well, I mean, you can redo the whole program, or if you trust that the formula works, right, then this is the PDF of X, evaluate root Y, and the PDF of X, evaluate minus root Y. But, right, because the PDF of X is exactly 1 on 0, 1, so this is 0, and this is 1. So the PDF of Y is 1 over 2 root Y. There you go, right? So it's not the square, it's a square root. All right, it's a square root. So again, let's just drive the message home. If you have a uniform 0 to 1 like this, then if you square it, then it looks like this. Right? It's not a parabola. So, right, not easy, okay? So that's why we need to use this tool to figure it out. Any question about this? All right. Yeah, we'll look at that later. So there you go. But this is a different one, right? We want to find the distribution of minus log. All right, so let's go through the steps here. What's the first step that we should do? The first step is to start with the CDF. Okay. Second step, replace Y with whatever you need to, right? Whatever Y is. So here Y is minus log of the uniform. Okay. Third step is to work out this expression, right? And then kind of isolate the U, right? So the third step, if you will, is isolate the x or isolate u, whatever, right? But I guess before that, right, I guess I missed step 0 that I told you to always do, which I guess because I kind of want to solve the problem quickly, I even fall to that. What should step 0 be here? Is there a step 0 in this process? What should we do before everything else? We should try to find the support of y, meaning the value that little y can take. Okay. Why? Why do we need to do that? The reason is it might or it will become relevant here at this stage where you have to deal with inequalities and shuffle things around. If you don't know what value you deal with, there might be a chance you make an error because right, inequalities you switch, right, and things like that when you shuffle things around, right? For example, let's say x squared less than equal to y, right, is equivalent to minus square root y less than equal to x less than equal to y, right? Something like that, square root y. So inequalities are much more, well, not much more, but are more involved, right, than equalities. So when you deal with inequalities, it's better, or it's not better. You must, right, know or be aware of the two quantities you're dealing with, so you manipulate them correctly. All right. So that said, right, what values can the random variable y take, big Y take here in this case? What values can it take? Well, what values can you take? U takes value from 0 to 1, right? What happens when you take the log of a number between 0 and 1? The graph of the log looks like this, right? I guess I draw my asymptote incorrectly, but right, like that. So basically, right, it hits 0 at 1, but right, it continues to minus infinity over here, right? So it takes on the range of value from minus infinity to 0. Right? And so if you take the negative of that, it will be 0 to infinity. Is that okay? Any question on that? So, right, now if we isolate the u, right, what is this in terms of u? U bigger than equal to e to minus y, right? Which of course is 1 minus e to minus y. Okay. Are we done here? The answer is no, right? Because for a continuous random variable, you have to find its PDF. So what you have found is its CDF, right? So to find the PDF, you would differentiate. So that's the PDF. Okay, any question with this? All right. So, well, right, part A, I guess we can do part A, but it's quick, right? What's the answer to part A?
One half.
Yeah, right, that's quick, right? The question is part B, right? But part B here, right? I would rather say with this, of course, it's meant for you to do it rigorously, but what's the guess here? If you have a uniform from -1 to 1, what will be the distribution of the absolute value of that? If you have a uniform from -1 to 1, what's going to be the absolute value of that? The guess here is uniform 0 to 1. Again, right, if you work with this for a while, you could guess this, but I emphasize, right, the guess here is limited to some cases. And the guess here does not mean for this problem even in particular, you can just guess and say, I'm done, all right? The reason is, for example, if you're so good guessing, right, tell me if I change this to -2 to 1, right, what would the answer be, right? So there, right? It is not really, right, that easy to guess, okay? It's about the symmetry of the nature and blah, blah, blah. So it's a guess, right? But you still have to do this in a rigorous way, which is start with the CDF. Oh, I guess before that, right? Step 0. What is a support? If x is between -1 and 1, then the support is 0 to 1, right? If you take the absolute value, a number between -1 and 1, you get the number between 0 and 1. Okay? So, right, little y here is in 0, 1. The reason is, right, we know that this is a positive number, right? So when you look at the absolute value and you want to work on the absolute value, right, it will become right. And the final answer is right. Not final answer, sorry. The answer is right for the CDF is that. Any question? Well, what can we do now? We will differentiate, right? Of course, right is 1. So it's a uniform. So the guess is correct. Any question with this? All right, I guess this is the last one, right? Again, if you feel like making a guess, go ahead. Is there any guess here for what y looks like? Okay. So what is the support of y? What values can y take? If x is between 0 and 1, then e to x takes value from where to where? From 1 to e, right? So for a value between 1 and e, right, probability y less than equal to that value is probability e to x less than equal to that value. And because the value is between 1 and e, right, I can take the log, right? Because it's a uniform, it's just log. Well, then what is a PDF? 1 over y. So who knows what that is? Just some kind of PDF from 1 to e. Okay. Any question about this? All right. So let's finish up our lecture. All right. Any question? So these are not on the need to know list. So these are things that I'm just putting here, right? So kind of to show you or to tell you there are random variables beyond the uniform, the exponential, and the normal, right? In this class, that's what you need to know for the continuous distribution, right? Uniform, exponential, and normal, right? We won't go beyond that. But obviously, right, the family of well-known continuous random variables are much more than that, right? So you have the chi-square, and the chi-square, right, starts out as the standard normal squared, but that is called the chi-square random variable with 1 degree of freedom. And the PDF, right, it's given like that. And notice I call that a claim. You will see the chi-square in a class like 481 at Rutgers, right? Introduction to Mathematical Theory of Statistics. And the point, right, with the chi-square compared to other random variables we've done before is notice how it's not defined directly as a PDF, but it's defined indirectly as a function of another random variable. That's the point I want to make here. This is its definition. Of course, right, you can define, right, a random variable in any way you want. You can define with a PDF, meaning you can start here and then prove that this is true. That's fine. But that actually is not the normal context where the chi-square comes up in statistics. This the chi-square comes up when you look at the sample variance, all right, in statistics. And so there you naturally have like the normal squared, something like that to begin with. So the reason why we bring this up is to make the connection with this topic, finding the PF of a functional continuous random variable. Meaning that for some important random variables, right, the definition will not be a PDF, meaning you don't have the PDF on the plate, right? Especially if you want to do statistics, you want to study statistics and whatnot. Statistics is full of random variables defined as combinations of other random variables, because that's how they work with random variables. And a lot of times the goal, or not the goal, but part of the work is to figure out what this is. All right. So that's why the techniques that we just went over is actually very important in a class like statistics. Right, and not the story doesn't stop there. You will have to sum or combine independent random variables to come up with other random variables, such as the chi-square with n degrees of freedom is a sum of IID chi-square with 1 degrees of freedom. So right there you have like summing independent random variables. A topic we'll look at in the joint distribution a little bit, and then also in the moment general function. Okay, and then the t distribution is defined as the standard normal divided by the square root of chi-square over n. And so, right, and so on. So basically, right, what we told you or what we show you are just the basic theory, right, or are the theory to work with some continuous random variables, but the story doesn't stop there, right? Beyond this, then you have to work with interactions of continuous random variables. You have to work with functions of random variables and things like that, right? So this is basically just scratching the surface, if you will, right? This is not the end of the story in any way. Any question? Okay. So let us start the next lecture. Which is about, right, showing distribution of random variables, which kind of like, you have seen some advertisement of that in the previous slide, right? So basically now we want to study, right, in a nutshell, the interactions of random variables. And so basically, right, or another way is to look at random variables in higher dimension, but it also contained implicitly in that this description is their interaction. I guess, yeah, a story that we will kind of repeatedly going over is, right, knowing how the random variables are given in multi-dimension has I guess a consequence, right, in how they interact. For example, right, if you have random variables distributed on a square, right? So, like this, right? Meaning what? That random variables, right, is a pair of two numbers, but they can be anywhere, right? So this is x1, x2, right? They can be anywhere uniformly on the square. But instead of that, let's say you have a circle, right? So it's a pair of coordinates that anywhere on the circle, right? Uniformly. Do this describe the same situation in terms of interaction? In other words, right, I guess well, we have not mentioned this word for a while now, but let's bring it back. Independent. Are they both independent in these two cases? Or in neither case they are independent, or one is independent, one is not? What do you think? The answer, right, will be here they're independent and here they're not. And the reason, right, is actually you could see the intuition. Basically, right, condition on a single value of x, let's say, right, x1, then x2 have the same distribution throughout, right? At least it seems like that. Again, right, we need more tools to establish this precisely. However, right, with the circle, you see, right, if x1 is out here, then the range of x2 is limited. But if x1 is in here, the range of x2 is wider. In other words, right, knowing where x1 is will have an effect on the values x2 can take. That alone, right, tells you that x1 and x2 cannot be independent. You understand? So yeah, right, the story that we'll get into here is twofold. On the one hand, right, it could be as simple as giving, right, a higher dimension, like 2 or more, right? And we'll just usually stay at 2. Like the joint distribution or how two random variables behave together on a plane, right? Things like that. But the story doesn't stop there because it will imply or directly what this means is the interaction, right, between these two random variables with each other, right, as described by the joint distribution. Okay, that's the goal that we'll get into. And also, of course, right, how do we find the individual behavior of each random variable given their joint behavior? Any question about this? All right. So just like the one-dimensional case, we'll split our study right into two subcases, and emphasizing that the world doesn't neatly right fall into these two camps, but this will just help make things easy for us. The first one, right, is to make sure to assume that all random variables involved are discrete. So basically, right, they take on a multidimensional values, but the values they take are discrete, right? So basically, like kind of grid points, right, in space or on the line, that kind of thing, right? Grid points, okay? And so if they're grid points, then what we require is the sum over all the grid points is 1, right? Notice now it's the sum over all coordinates, right? All coordinates, not just a single dimension, right? But the story is the same, right? If it's discrete, you sum over all possible values, you should get 1. Right, so there you go, right? It's basically the grid points, right? And the height here are the mass function at each grid. So, right, a jointly discrete are just spikes over the grid points. Okay. And no smooth surface. The smooth surface will be the joint PDF, right? I guess let's just show you the joint PDF and then we can go back to this. Because, right, so there, right? In contrast to the spike, right? The joint PDF, if they are jointly continuous, will be a smooth surface over some support, right? Some region. So the picture you're seeing here, right, is the joint PDF of joint normal distribution, right? So I'm not sure though what the description here is. Looks like a tent. Tent is not the right word, right? Whatever, right? But this is a joint normal distribution. Okay. But now let's go back to the jointly discrete case and see what's going on. All right. So, right, just to kind of get your thinking going on, right? Let's take a pair of random variables where x takes on 4 values and y takes on 3 values. What does it take to completely describe the behavior of x and y? What that means, right, is you have to fill in 12 entries of legal values, right, to describe the joint distribution of x and y. Well, what rules does it have to follow? Simple, right? These are probability, so they must be non-negative. And when you fill in these values, you might have to make sure that the total sum of all these values is 1, right? And think of these 2 questions, right? But here's an example, right, of such a table, right? So 4 values for x, 3 values for y, the total sum, right, is 1. Okay. So notice, right, each of the entry here will tell you, right, probably x equals to 2, y equals to 2, let's say, probably x equals to 4, right, y equals to 3, right, and so on, right? Any question about the table so far? Now, right, pay attention to these 2 columns lying on the margin, right? And that's why, right, in this context, they are called the marginal distribution, right? How do we get the margin? Well, simple, right? We would sum across the rows or sum across the column, right? Well, if we sum across the rows, what are we doing? We sum across the rows, we sum for a fixed value of x, right? All value over all values of y. So what we end up is getting the particular value of the probability of x taking all those values. So this is the marginal of x. Similarly, right, when you sum across the rows, you sum away the x and you get the y to remain. So that's a marginal of y. Right? So that's how you get the marginal in general, even for continuous random variable. But it will become a multiple integral, right? Instead of a sum. So any question? All right, so let's stop here, right? And remember that the midterm is on Friday, right? So the first 25 minutes will be Q&A, and then the exam will be after that, right? Just like midterm one. All right, so we'll continue our lecture on Monday, and I'll see you on Friday or Monday, right? Depending on whether you want to show up for the Q&A session. All right,
Professor,
yep.
would it be possible for you to share like a midterm test from previous years or something?
You don't need that. Just start the homework.
Okay, okay. All right, all right. Thank you.
Yep.